This is the video recording for Algebra 2, Unit 5, Lesson 5.6. All right, so now that we understand what polynomial functions are, what they look like, how to find those roots or zeros, we're going to look at how do we graphically represent these different functions here. All right. So now we are aware of two different types of functions, okay, and then the graph has some special features here, right? We're going to talk about that here. We've introduced it a little bit here, but we're going to really hit this home in this unit. So there are some features here that it can always tell us, right? Especially knowing those parent functions, we can pick up on some trends here. All right, so one key thing that the graph does show us is it tells us what degree that the function is and how it acts as a set overall, being what's the end behavior of the graph on the negative x side and the positive x side. All right. So paying attention to things on graph, right? The end behavior, like I just pointed out, how many hills and how many valleys does it have? Where does it cross the x-axis? Where does it cross the y-axis? Does it cross the x-axis? All of that stuff will tell us a lot about the nature of the equation. All right, so this graph here represents a cubic function. Right, it represents a cubic function, and there's a lot of things that could have told me that, right? Knowing what the shape of the other two and doing process of elimination, or picking up on things within the graph, right? A lot of key hints there. All right, but moving forward here, we talked about this thing called end behaviors. All right, so again, what happens when x goes on forever and ever negatively and goes on forever and ever positively? That is something we call end behavior. All right, so what we're going to look for is values that we can identify that's going to tell us the end behavior. All right, so looking at this though, the end behavior for both of these, they both go in the same direction. So whether it's both going up or both going down, regardless, they're both going in the same direction. All right, and what's common between these two is this is an x squared and this is an x to a fourth. So the degrees of both of these equations are even. All right, this guy here, one end goes up and one end goes down. Sorry, I was looking for both has one end going up and one end going down. But regardless, one's up, one's down. Okay, and what's similar between this is an x and this is an x cubed. So the degrees are both odd on them. They're both odd. Okay, so the relationship between it is if you've got an even degree, the end behavior will be the same. And if you have an odd degree, the end behavior will be opposite. Okay, so by looking at functions, we can then generalize if it's going to be an odd or an even number, right? Which is pretty. So how do the end behaviors of these two graphs differ? Right, one is same, right? Both going up, both going. Oh, sorry. These are both going in the same direction, right? But one's going up. One's up and one's down. Okay, so both ends are going in the same direction, whether it's up or down. Okay, the equations of these two functions have many differences, but which of the following is true? All right, what's true is that the leading coefficients have opposite signs. If you look here, this is positive 2x squared, this is negative x to the fourth. All right, so both of them have even degrees, but what's different between them is the leading coefficient there. All right, again, same thing here. What's different about these two behaviors? The right side of the first graph is positive and the right side of the second graph is negative, right? One's going up, one's going down when you get to the far right side. All right, so then what's different between these two, you probably could have guessed it. This is a positive value and this is a negative value. All right, so the leading coefficients again have different signs. All right, so the pattern here, is that this one, if it's got an even coefficient and a positive value, it's going to go up. If it's got an even coefficient and a negative value, they're both going to go down. All right, and then looking here, if it's got an positive leading coefficient and it's a odd number, it's going to end up positive, right? Okay, and if it's a negative and an odd, it's going to go down, right? So it's going to start up, go down. All right. And then a better way of seeing all this is, okay, if the degree is even, they're both behaviors are going to be the same. If the degree is odd, they're both going to be opposite. All right. And if the leading coefficient is positive, the right-hand side is going to be up, right? And so that means both sides of the graph are going to be up. If it is negative, but it's still even, that means they're both going to be pointed down. If the degree is odd and it's got a positive leading coefficient, the right-hand side is going to go up while the left-hand side goes down, and obviously opposite for the negative coefficient. All right, so if we look here, we've got negative 3x to the fifth. All right, so it's easier for me if I start on the right-hand side. So this is a negative value, negative 3. All right, so negative 3 means it's going to have the right end of the graph is going to be going down, right? It's going to be going down. All right. The left-hand side, since it's odd, is going to be doing the opposite behavior. So it is going to be going up, right? That one's going to be going up. Okay. So the way that we can describe end behaviors, right, to use some mathematical terminology that you're going to see again moving forward with these classes, is shown like this. All right, so this is saying as x goes towards infinity, that's what it's saying, as x goes towards infinity, then f of x, our relationship here, also goes towards infinity. So if you look here, this is our positive x infinity direction. This up here would be our positive y infinity direction. So it's saying as x keeps going this way, this way, this way, then y is going to keep going this way, this way, this way. All right. So perfect. It just showed it, right? And all that means by negative infinity is just a really large number. Okay. So then this one's showing... Okay, this one's showing that as x goes towards negative infinity, then y is going to go towards negative infinity. And you should be able to scroll over these and read what these mean, okay? But this notation here is called limit notation, all right? It's called limit notation. And how we write that is limit of f of x, right? So our limit on the y values we can get is going to go towards whatever this is, right? So it's going to be negative a really large number while x becomes negative a really large number. Over here, this is again saying y is going to go towards infinity as long as x goes towards infinity, right? That's what that one's saying there. Okay, so then here we're already familiar with finding the x-intercepts being 0, right, and those different roots. So now we're going to just rehome that in and also find our y-intercepts. So to solve our x-intercepts, we know how to do that, set that equal to 0 and solve, so we can get that there. For solving our y-intercepts, we're going to substitute in 0 for x, right? And then restating our answer. So for f of x is equal to x minus 9, the x-intercepts are, and the y-intercepts are. Again, just re-summing it all up, okay? If you had to write this in a word problem format. Okay, so I'm assured we can all do this here, but x-intercepts first, find the y-intercept here. Okay, you could maybe look at it and just know, but basically you're going to plug that in for 0. You're going to get 24, so that is our y-intercept. All right, doing our x-intercepts, we'll start with our rational root theorem, get our p's over our q's, figure out the sign changes, what our possible roots are going to be. All right, and then we'll test some of the roots like we just went over. So here we test 6. We find out, hey, it's all positive, so that is going to be an upper bound, so we don't even try 8, 12, or 24. All right, so then we find out that we can use synthetic division to find another factor. All right, so we can find another factor here. And we can look at 4, move down, and oh, that one's a factor. And something I want to point out here is that if you look at our P and Q values, all the list of rational theories, this is all saying plus or minus, plus or minus, plus or minus. Okay, so when we tested positive 6, we're only throwing out the positive 8, positive 12, positive 24. All right, so what you noticed here is it shows you negative 8, negative 12, negative 24. All right, so it shows you that you're still having those as potential roots because, again, we only had our upper bound that didn't also cut off our lower bound. All right, but anyways, we found out 4 is a root, then we can solve our remaining quadratic equation, so we've got our list of roots there. All right, so then what we can do is plot those points, right? Those are key points that we want to plot on our graph, and then knowing the relationship of now our positive coefficient, positive leading coefficient, we know that it is a odd function, so the right hand's going to be up, right? So we know that our graph is going to have this kind of windy shape here, again, highlighting the key points of our x and y intercepts. All right, so practice here. You guys can do that on your own. And then we learned about multiplicity, all right? And what that means is it just shows up on your roots multiple times, right? 2, 3 times, whatever. But we only show it graphically in one place, okay? We only show it crossing the x-axis that one time, all right? If we have something like the above here, we have x plus 1 squared, so that means that we have -1 twice, so what we say is that that's a root with multiplicity of 2, or you could also call it a double root, all right? And multiplicity can tell you things about a graph without actually having to cross the x-axis twice. So if we look here, though, okay, 2 is a root with multiplicity of 1, and -1 is a root with multiplicity of 2. All right, so looking here, trying to see if there's anything that you can pick up on a pattern here. All right, now this one here had 1 with a multiplicity of 3. So maybe you can see something, maybe you can't. Let's look at what the next slide's telling us here. All right, when the multiplicity is odd, okay, when the multiplicity is odd, it crosses the x-axis. When the multiplicity is even, it only touches the x-axis. So look here. All right, this one just touched the x-axis, right? And this one here actually crossed. This was our one with multiplicity of 2, and this is our one with multiplicity of 1. So if we play this video here, look, this is our multiplicity of 2. It only crosses, okay? If we turn that into a multiplicity of 3, okay, similar graph shape, but look, it actually crosses the x-axis. I know it's hard to see. It looks like it just flattens out and then dips. All right, but if we zoomed in here, it would cross at that x-axis of 3. Or sorry, at x equals -1. All right, but then again, if we go down to 4th now, this re-flattens out here. Okay, it doesn't actually cross the x-axis, but when I turn it to 5, it does. So odd multiplicity will cross the x-axis, while even multiplicity will just touch. All right, so looking at this here, this is saying this one would have a multiplicity of 1, and this one would have a multiplicity of an even number, right? A 2, a 4. This here, both of these would have a multiplicity of an even number. A multiplicity of an even number. So if I'm looking here, 2 and 2, there we go, right? This one has a multiplicity of an even number and an odd number. An even number and an odd number. So then what we would have to do is, if it looks similar to these guys, you actually have to go in and look, and you can't just guess, right? So this is saying x plus 1 has a multiplicity of 2, right? So this is saying x minus 1 will have a multiplicity of 2. Right? Whereas this one is got its multiplicity at x equals 2. Right? So paying attention to those minute differences here. All right. So we learned about these things called extreme values, right? So our maximums and our minimums here. All right. And when we look at our even versus our odd, okay, our even versus our odd, we will have an absolute, right? We will have an absolute we will have an absolute minimum here if we have an even function, right? An even function. But you notice here, we don't actually have an absolute, we only have relative values. We only have relative values because it has infinity going in both the negative and the positive directions. So if we look here, the degree of the polynomial tells you something extra about these extreme values, right? If the polynomial, oh, and that's another one, right? So another one. If a polynomial function has a degree of n, the graph will have at most n minus 1 relative maximum or minimums, right? That's another thing. All right, it'll tell you the number of bumps in your graph. So this is a 2nd degree function. This has 1 bump. 3rd degree has 2 bumps. 4th degree has at most 3 bumps, and the 5th degree has, again, at most 4 bumps. This isn't saying that a 5th degree polynomial can't just have 1 bump, but if you have 4 bumps, it has to be at least a 5th degree or higher polynomial. All right. So then locating our relative versus our absolute. So if we look at A, D, F, and H, right? A, D, F, and H. All of those are minimum values here, okay? But only H is the lowest value, all right? So H is the lowest value. So that one would be considered our absolute minimum, while the other ones would just be relative minimums, all right? If we look at our max values, we have A, C, E, G, and J. Oh, and apologize, I left out J in the minimums. Okay, so that J would also be a minimum. But I here is the absolute highest part of the graph. So all the other bumps are considered relative maximums, while I here is the absolute maximum. All right, and that's what this guy's saying here. The relative maximums are those ones that were moderately high, right? Well, the absolute maximum is considered the top value there. All right, how many extreme values are there? There are 2. Okay, there are exactly 2 here. All right. Oh, sorry. Apologies. At most 2. All right, good. They corrected me on my English there. All right, it can have at most 2. I was actually looking at the graph here. Okay, so but this graph here has 2 extreme values, but based on just the equation here, based on just the equation x cubed, right, it can have n minus 1, so 3 minus 1, it can have up to 2 extreme values. All right, since it says defined for all real numbers, meaning it goes on and on forever. Okay, it has no absolute extreme values. Has no absolute extreme values. But the relative values are obviously right there at -1, 0, and at 1, negative, looks like -4. All right. So then there's this thing called intersection points. So it may not be obvious here, but they have this thing called an inflection point, and it's where the graph changes. It's thing called concavity, right? And concavity means the way that it is curved, right? So the video will go over it, but you have concavity up and concavity down. So let's watch this here and learn about inflection point.
The region of the graph that curves downward is said to be concave down. The region of the graph that curves upward is said to be concave up. The point at which the concavity changes is called an inflection point.
Right? And again, this is another way that I remember this, that concave up like a cup, right? It's shaped up like a cup. Concave down is down like a frown. All right, so this inflection point is the point where it stops having this concave down form and goes to this concave up form. All right, so now then we can put it all together and we can actually produce an entire complete graph using the cues we know from the equation and how that translates to our graph. So when we're looking at this
First, find the x and y intercepts. To find the y-intercept, substitute x equals 0 into the function and solve for y. The x-intercept is found by factoring the function and finding its zeros. Now, move on to the end behavior of the graph. Since the leading coefficient of the graph is positive, and this is a 5th-degree polynomial, the right side points up. We write. Because the function's degree is odd, you know the left side will behave oppositely, pointing down.
All right, and again, to read this is saying as f of x, so as y is going towards positive infinity, x is also going towards positive infinity. Or as x is going to positive infinity, right, then the y value is also going to be some positive infinity value.
This can be expressed as, you can now sketch these behaviors on the graph. What happens between the points that you have drawn so far? The trick is to make a table of x-coordinates between the ones you know and evaluate the function at these new values. Then you can graph these points too.
Okay, and again, those are just relative points, about halfway between. So that would be as if you didn't have access to your graphing calculator. All right, you would plot them, get some relative values, and then draw your general shape from there. Since you have the ability to type this into your graphing calculator, okay, once you've identified those key points where it has to cross, and you've identified if it needs to go in the positive or the negative direction going left and right, okay, you can plug this into your graphing calculator and see generally where those lines are going to be,
points.
right? So if
you can use your...
There we go. Okay, so then you could generally see, and by generally I mean you would be able to see that this first bump here is higher than this bump, and this second bump is lower than this bump. All right, so you could be able to do some general things along that line and sketch your graph.
Calculator to estimate the locations of the extreme values and the inflection points.
All right, so then once you've plugged it into your graphing calculator, like he said, you can do that button calculate, right? So that would be second calculate, and it'll ask you if you want to calculate your max, your min, your points of inflection, all this wonderful stuff here that your graphing calculator lets you do, right? And then depending on the version of your calculator, it might have other instructions like giving a left bound or a right bound, and all that's talking about here is if I'm looking for this, maybe this 0 value here, if it's asking for a right bound, that would just be something over to the right of the graph. And then a left bound would be something over to the left there. All right. All right, and then lastly there, I think they talked about it, I might have skipped over it.
Calculator to estimate the locations of the...
Okay, so here is talking about where it's going from up cup to down frown. Okay, so you see these blue that are highlighted? Those are concave down because they're frowning. But as soon as we hit the x-axis here, all right, this right here are points of inflection because it goes from being down to being concave up, right? And then this one is a concave up to concave down. All right, so those are our points of inflection for this graph here. All right, now it's not always that it is at the perfect x-axis, but we'll talk more about that later. All right. So end behaviors, again, talking about how the left and the right-hand side of the equation behave, and I'll let you read through these rules because there's a few of them here. Intercepts, right? Intercepts, you can calculate the x-intercept. We worked a lot with that. Y, you just plug in a 0 value and then solve. And then multiplicity. So if you have more than one root at the same value, we don't show it graphically. We just show it once. But that multiplicity is going to tell you whether it crosses the x-axis or if it just touches. And then extreme values, again, those are those hills or valleys or bumps, whatever you want to call them, where you can have an absolute and a relative of the max and the mins. All right. So then looking here, based on this graph, you know that since they're both going up, you know that it's going to be an even degree. Okay, you know that the degree is definitely going to be even. And since they are up, right, that you know that the leading coefficient is positive. So the answer to that would be B. All right, looking here, what are the y-intercepts and x-intercepts? Okay, so for here, we would just solve and plug in here. All right, so you would solve, you'd set y equal to 0 for one of them, and then you would set x equal to 0 for one of them, and then solve from there. All right, this is asking, does this function cross or touch the x-axis? All right, and in this one, x minus 2, and that quantity is to the power of 4. Since that is got a multiplicity of an even number, that means it's just going to touch. Right, it's just going to touch. If this was x minus 2 to the power of 3, then it would be crossing, right? So it's only touching. Right, through the graph above here, this is our relative max and this is our relative min. We have no absolute. All right, and when it's talking about and it's asking you for a single value, what it's saying is what is the y value? Okay, so the relative max and min, the relative max is y equals 8, and the relative min is y equals 0. All right, so if you ever see it with one value, that's what it's talking about. Okay, so then quickly here, looking at our study guide. All right, these are our rules for our end behaviors. Again, super, super important. Keep that on you, or try to pick up on those patterns and hold those down in your memory bank. But those are going to be really, really helpful. All right, looking at this here again, we can tell that it's going upwards forever and ever and ever. And what this is saying is use infinity notation. Okay, so infinity notation. So this is our infinity notation, if I didn't mention that earlier. Basically saying, all right, what is y doing when x goes towards infinity or negative infinity? All right, so x positive infinity is over here, and what this is saying is x goes towards infinity, our output y is also going towards infinity. All right, this one here is x goes towards negative infinity, y is also going towards positive infinity. All right, so that would be how you answer that question there. Solving for x and y intercepts, again, plugging in for zeros and then solving the missing equation. All right. And then this is saying here, match each graph to its correct function. Okay, so again, keys you're going to be looking for is multiplicity, right? If it's even, it's going to touch. If it's odd, it's going to cross. You need to actually maybe solve for some of these values here. So knowing that x plus 1, right? That's saying that at x equals negative 1, you're going to have a multiplicity of 2. So you're going to have a bump at 2. Or I'm sorry, you're going to have a bump at x equals negative 1. All right, so things along that nature, picking up on those trends. And then again here, the number of extreme values is is the degree number for the polynomial minus 1. So this would be 3 minus 1, this would be 4 minus 1, and this would be 2 minus 1. All right, so those are some of the practical rules there. And again, really trying to bring it all home here and figure out how to draw graphs of polynomials or identify those graphs of polynomials based on the equations there.